Technology Varanasi in India. So we have a participant here around, I think 60 plus people sitting here, so waiting for your presentation. So thank you very much. So Dr. Hong Hao is actually, now he is also associate professor in the Zhejiang University of Technology. Am I right? In China. And then he going to be postdoctoral research associate at Queen Mary University of London. So yeah, he basically going to be my postdoc, and then today I invite him to give some how to say experience and also training on the simulation for defects and microstructure using. Sorry, I may need to repeat again. Okay, Hong Hao, I probably repeat again because we have some recording. I did record the team, I believe. Now, yeah. So let me introduce yourself. So you Hong Hao, Dr. Hong Hao, Associate Professor in Zhejiang University Technology in China, and then he's going to be postdoctoral research associate at Queen Mary University of London. So today I invite him to give a talk on the simulation of defect and microstructure using CFD ANSYS FLUENT software during melting certification from casting to additive manufacturing. So yeah, the floor is your Hong Hao, and yes, please. Can you speak now?
Yes. Let's continue. What is CFD? We know that CFD is short of computational fluid dynamics. It's a branch of fluid mechanics. It's a numerical method to solve and analyze problems involving fluid flow. And I think that key aspects of CFD include the four parts. First of all, I think is the types of fluid flow. CFD can simulate various types of fluid flow. For example, it's laminar flow and turbulent flow. And what's the difference between the two kinds of flow? I think is that it's the Reynolds number. For example, if the Reynolds number less than 2,000, I think it's maybe the laminar flow. And if the Reynolds number higher than 4,000, it may be the turbulent flow. Between 2,000 and 4,000, it's the liquid flow shows it is a transition state, I think that. And also, the CFD can simulate the compressible flow and the incompressible flow. And the difference between these two kinds of flow, I think, is the density. If the density can change during the flow, such as like air gas, it must be the compressible flow. However, for our simulation, incompressible flow is very usual. For example, we take the melted metals into account, and other incompressible flow, such as water flow. Also, in CFD, the fluid domain is divided into small control volume. We call it cells or mass. And the governing equation of fluid dynamics, such as...
Do you move your slide? You are in the...
No.
Not yet.
Yes. Such as Navier-Stokes equation will be the main governing equation of fluid dynamics. And the third one is the numerical method. I think the CFD always uses the method like the finite volume method. We call it FVM to approximate solution to solve the governing equations. CFD is widely used in various industries, including aerospace, automotive, civil energy, and something like a chemical reaction set. It's used to optimize the design, configure performance related to fluid flow, and heat transfer and chemical reaction. And next is in this slide, I want to show that common CFD tools. There are several CFD tools. Some of them are famous to us. For example, the ANSYS FLUENT and console overform. Some they are widely used in different industries. Some of them are only used in their specific area. For example, the CFX are widely used in pumps and science industry, and some CCM parts are always used in shipbuilding industry. In today's lecture, I want to introduce the ANSYS FLUENT. And the ANSYS FLUENT is widely used in industry. actually. It's a world-leading computational fluid dynamics software. It's developed at the MIT in 1980 and commercialized by Fluent Incorporated in 1983. And Fluent has been widely adopted across industries such as aerospace, automotive, energy, and chemical engineering. During 1990s, Fluent gained rapid popularity due to its robust physical modeling capability and ability to handle complex geometry. In 2006, it was acquired by ANSYS, becoming a key component of ANSYS product. Later, Fluent has cutting-edge technology like high-performance computing, cloud computing, and so on. By 2020, the integration of artificial intelligence, we call it AI, machine learning, and GPU acceleration has enhanced its simulation performance, enabling faster, smarter, and more accurate solutions for engineering challenges. Fluent continues to set the standard in CFD, driving innovation and delivering powerful tools to tackle complex problems in modern engineering and scientific research. Here I will show some simulation on fluid flow numerical calculated by Fluent. First of all is the common vortex speed. It's a periodic pattern of vortex that following a cylinder expected linear numbers. And the second one is the mixed simulation of gas and liquid. In this case, the volume of fluid method is used to check the interface between liquid and gas. And the third one is about the fluid flow in pairs. The fluid can be used to investigate the fluid flow in the turbine machinery in parallel. It is important for understanding flow patterns in this case, and engineering can use this simulation result to design the pump or such like this component. And the fourth one is about the simulation airflow around the building. It's important for understanding window behavior and its impact on building. This CFD simulation analyzes how air flow over around between the buildings, providing insights into wind patterns, size distribution, and potential turbulence zone. Additionally, aerodynamics always plays a vital role in the design and performance of aircraft. analyzing the force generated by airflow. Flow field simulation provides detailed insight into the behavior of air around the aircraft body, wing, and control surface. And for me, Microstructure area is mostly focused on the additive manufacturing. This shows a typical additive manufacturing process. We call it laser powder bed fusion, LPF. These are typical of additive manufacturing that use a high powder laser to selectively melt powdered material layer by layer. And then we'll build a solid object from a digital 3D model. The key steps in LPD process, including the powder layering, which means a thin layer of fine metal powder is spread on a filled platform. And then the laser will remelting the powder particles. And another layer of powder is spread on top of the previous one. The process repeated till the object layer by layer until it is fully formed. After that, it typically undergoes further process such as heat treatment, surface finishing, or machining to achieve final required property and dimensions. And here is our simulation about the metal pool evolution during LPVF. We can see the metal pool, we can investigate how the metal pool forms, and it will move along the laser beam. And also in this case, we can see the metal pool and the densified grain growth during the metal pool solidification. And we can also see the metal segregation during the metal pool solidification. And another additive manufacturing process is laser direct energy depositing. So when it uses a focused laser beam to metal and deposit material. Typically, the metal powder or the wine onto a substrate to create parts layer by layer. We call it LDD is sort of laser directly energy deposition. LDD allows for the deposition of material directly onto an existing part or substrate. It's widely used to repair coat application and create a new component. Here is a video recorded by recorded by a camera. We can see the powder flow from the nozzle and how the particle is bounded by the metal pool and how the particle into the metal pool and the melted. And based on the experiment, we also do some simulation about the metal pool evolution during the LTED process. Here is temperature field evolution, also including the velocity, also including the metal flow in the metal pool. And this is microstructure evolution during the LTED process. Okay, let's back to the ANSYS FLUENT. All above simulation cases are calculated by the ANSYS FLUENT, and we know that if we want to make the numerical simulation, we should get the May-Summerlin equations. In ANSYS FLUENT, the May-Summerlin equation is presented here, and the computational domain is always divided into a series of control volumes, and the general composition equation for mass, momentum, energy, and species are solved on each control volume. And for this Summerlin equations, there are 4 parts. First one is the unsteady term, and the second one is the convexity term, and we call this one the diffusion term and the generation term. And if we want to investigate steady simulation, which means the physical phenomena is not changing with the time, and so the unsteady term will be omitted, will be neglected, and the Summerlin equation will become like this. And if our simulation is focused on a solid domain, which means there is no flow, fluid flow during our simulation, and the main Summerlin equation will become like this. We will neglect this one. And also, if we want to simulate like the steady state conducting in a solid domain, also in this simulation without consideration of any heat source, which means this one will be neglected, and the main Summerlin equation become like this. So, to us, if we want to make a simulation which should get or should know the Summerlin equation firstly, and then if we do that, we can do the simulation in FLUENT software. There are 9 steps for make a specific simulation. First of all, we should define the goals of our simulation. For example, if we want to do some research on our additive manufacturing, we should know what parts are what part we want to focus on. For example, if we want to investigate the metal pool, we should use the case focus on the metal pool or substrate or the sample. If we want to investigate the flow state of shadow gas in the chamber, we should use a case focus on the shadow gas. And so different flows in the different simulation case or different simulation case. Also, we should prepare different math or geometry file or something. And after that, we should create a geometry and prepare the math file and then the physical problem, such as we select the models and also input the material properties and also want to set the boundary conditions and so on. After that, we can start the calculation and get the result and at last we can review the computational results. Also, I think that the most important thing is update the model. Because if we want to get a precise simulation result, we want to update the model maybe several times, maybe for a long time. Also, we want to compare the simulation results to our experimental results and to check if the simulation results is in good agreement with our experimental results. And during the simulation, ANSYS FLUENT also provide important function. We call it UDF. UDF is sort of user-defined function. It's a function written by user in language C, which can be dynamically linked with FLUENT. And why we use UDF? It's because the FLUENT provides because the standard interface cannot simulate all user-specific needs. For example, we want to change the boundary conditions, such as if the boundary conditions varies with the temperature or some pressure and something else, or the standard interface cannot provide such function. So we want to write a function using the language C, and the FLUENT will compile this code and and list this function. And also, here in this slide, I want to show during the simulation where we can add or link the PDF. For example, we can make initialize use this macro to define the temperature or define the pressure before we start our simulation in the freezer domain. Also, within the loop, we can call for this adjuster macro to modify the value in the simulation domain. Also, we can use soft to change the simulation term, which I mentioned in previous slide in the Downey equation. And also we can update the property of material or the boundary conditions, and at the end we also can record the value of the simulation domain. And here I want to show is some example of defined macros. We always use this one, and this one is always be called for the simulation. It's used to initialize the field variables. And also this one, the properties always used to update the material properties. And this one we can change the time steps for simulations. And in this slide, it's another macro for geometry and time. And we can use this macro to get the specific fields. We can get the value stored in the specific volume. For example, using this macro, we can get the cell volume, and this one we can get the coordinate of cell centered in arrow axis. And these three ones are always related to the time. For this one, we can get the actual time during our simulation. And this one, it will return the time step during our simulation. And this one is time step size. And in this slide is for the macros of physical parameters. And for example, density, pressure, and this one is mass fraction, and so on. And later I will show a simulation case from geometry, how to get our max file, and then how to set up the model, and get the results. And the case is about in this case, there's a pump. The diameter is 2 millimeter, and the length is 10 millimeter. And we want to set the inlet velocity is defined as this equation. And in the standard interface of FLUENT, we can only input a constant value. But in this case, the inlet velocity is provided with the y coordinate. So we need to use the UDF to write this function. And we will use this macro and this macro. This one is used to obtain the center point of the inlet. And this one is after we calculate the value, and we will return the value to this macro. And this macro will set the value to the boundary of this simulation domain. And the first of all, we should prepare the code, and then we should compile the code and focus the code. Here is compile the code and focus the code. And after that, we can run the calculation and get the result. This result is the inlet velocity is 10 meter per second, and this simulation result is the inlet velocity is based on this equation. And I will show the whole process of this simulation case. And I created the slide first. And
yes, it will show the real FLUENT interface that you can look at how set up it. So it's first case is simplest that you can understand how we set up this thing if you're not familiar with FLUENT software. Any of you here use FLUENT for your research? ANSYS, FLUENT ANSYS. No? Oh, you.
The geometry and make the match file.
Yeah, please note that it's not the FLUENT case for additive yet. This is just the beginning. This is what you will see, right? I think.
And first we should create a geometry and the first point and the length of the tube is 10 millimeter, and the diameter is 2.
So create the geometry, I believe.
After that, I will create the line.
So I think the screen is dark, so we can't. Oh, okay, yeah. We saw the yellow line, yes.
Yeah. After that, we can create the face. In this software, we created the geometry from pointer, line, face, and volume. Step by step. Yeah, and then we match the face, and after that we should define the boundary name of this geometry, and the inlet is one, the outlet is one, and the wall, top and the bottom. And after that, we should define the simulation domain. We can choose this, if this simulation domain is fluent or solid. In our case, it is fluent. And after that, we can export. Export the map. And then we call it the map file as well. Copy the map file and to the okay, we can extend this one.
So the first step is to create the mesh, and then you export that to import in the calculation. I mean, run folder, I believe.
Yeah, and then we started the ANSYS FLUENT. Here is the interface, the starter interface. In our simulation is 3D. Here we can choose the dimension. Our simulation is 2D, so we choose the 2D. And here is the double precision. In ANSYS FLUENT, you can choose double precision, or it's the single precision. The difference between this type, I think, is the value of the value stored in 4 bytes or 8 bytes, I think. That's the only difference. And here we can choose if this simulation is serial or parent. If we choose this one, the simulation will run with number of process. And then here we can choose the serial. And then we copy to here. And then start. The version is a little older. Now the latest version of FLUENT is 2023 or 2024. My version is 14, 10 years ago. And but the function is always similar. First we near the max file. This one. Here is the max file. And because when we created the max file, there is no unit in that software. Here we should change the unit. Because in our simulation is the unit in our simulation is millimeter, so we should change millimeter here, and so the figure is 10 millimeter long and 2 millimeter. The diameter is 2 millimeter. And here in our simulation we are sized, so we just give it as sized, and if the fluid flow varies, we can choose the transient. Then in this case it's laminar and only one phase, so the multi-phase is closed. Also in this case there's no energy transfer, so the efficiency energy equation is closed. And the material is air. Also we can choose some other material. There is a fluent database in this software. For example, this one is water, liquid water. In our case it is air. And in this interface, we can change the material such as air or water liquid, but in our simulation is air, and keep it as air. And then the most important is the boundary condition. In the inlet, we set the value is 10 meter diameter. Also, we can use this menu. In this menu, which means we can define the x direction velocity and y direction velocity. Here we can use the x 10. It's the same. Same to this function. And yes, and that's all. And we initialize and run it.
Right. Okay. This is the velocity. Oh, sorry. This is the velocity result.
No, it's the result here.
Sure.
Yeah, this is the velocity result, and we can see the pressure explosion, and we also can do some support some. If we really want to know what's the velocity value along this direction, we can select the inlet and the direction is here, and it's 10 meter per second.
Right.
Yeah. This is a single case, and also I will show how to use the UDF to change the united velocity with this function, and there's another case which I explained.
Yeah, so this is just basic setup, and then if you want to demonstrate, yeah. So I think, shall we move to the first cases, and then we leave last two for the next session? So I think probably, or anyone want to see how we implement the user-defined function? Yeah. Or you want to be okay? Can you show quickly? This is user-defined function, right? I think this is a code that we talked about. So write in C language. Yeah. Hong Couch.
Yeah. In this case, we want to change the unit velocity. So we should write code. It is code, and we should define the diameter is 2 millimeter, and define a float value. And this area will be used to store the coordinate around the y direction.
Yes.
And and we will group the boundary of inlet and get the specific field, and then get the coordinate of the field, and store in this area, and this one is one coordinate, and we already know that x the arrow always from 0 first, and then we use this function to calculate the inlet velocity, and then back to the boundary condition, and assign the velocity. Here I will show how to compile this code and link to the point. Here is the code, and start the ANSYS FLUENT software, and use the match, and change the mix.
Yeah, repeat the same, but now we're not going to define using the constant velocity like before. But later we will impose the boundary condition with the function of y. Yes, please.
The same, and you just and we should compile the code, and add the code and build it, and then load, and you can we can see the x velocity is loaded in our software, and then we can see there is velocity here. We can choose this one, and it means the code is linked by the software. and then we click OK
Yes.
and inside and then run. And we can check the result. What's the difference between these two simulations? Here is result and we can plot. Yeah, it's different to our previous simulation, which means the inlet value has been changed by the code.
Yes, it's changed from the planar to parabolic velocity profile.
Yeah. Here is different result between these two simulation cases.
Very cool.
Okay, then let's continue.
Yeah, shall we pan like this? So we have 3 cases. So you will show from next half an hour on the first cases, and then we show the next 2 in the next session. Is that okay? Is that your plan?
Any questions?
Any questions so far?
Yeah. Or I will continue.
Yes, please. Yes, please. Yeah.
Okay. Next one, I want to introduce 3 complex simulation cases. First one is about the solidization of large-scale ingot. Large-scale ingot always use used to fabricate the rotor component, and the rotor component always it is an important part of power plant or steam turbine, and the ingot always will be fabricated by pouring metal into a model and solidified. Because the ingot is too big, the weight of the ingot, I think, it's over 10 tons. 10 tons, about 10,000 kilograms. In our simulation, I will present 55 tons. And after the solidification of the ingot will take 1 week or more than 1 week time to solidify after the liquid poured into the mold. After that, the ingot will be forged, turned, and machined. Finally, will be assembled as a rotor component. And because the ingot should take a lot of time to solidify. The liquid in the mold will flow from here to there under the thermal fluid buoyancy force. So under the solidification, the ingot always will be cut, and we can find micro segregation in the center of the ingot. The macro segregation is an even element, uneven element distribution on the macro scale of ingot. It's an undesired effect of the solidification, and it's difficult to eliminate by the downstream process, such as the forging, heat treatment. It's difficult to eliminate it. As all we know that the typical metal segregation in the center of the ingot include the top positive segregation and bottom cone-shaped negative segregation, and also in the center of ingot will appear V-shaped channel segregation, and also A-shaped channel segregation in this area. And our work is to build a numerical model to reproduce all kinds of this macro segregation. And during the ingot solidification, there are several physical phenomena here, such as shrinkage, because the density of liquid and solid phase are different. So, as the solidification progress, the liquid will be the air will be sucked from the top of the ingot, and finally the seepage cavity is formed in the top of the ingot. Meanwhile, the nucleation are always occur in the center of the metal, and with the growth of the grain, the grain will move from top area to the bottom area, and finally accumulate in the bottom of the ingot. Additionally, the chromium always grows against the border wall and grow into the ingot center. During the growth of the chromium grain, they have the ability to catch the liquid acid grain. And if the tip area of the chromium is full of liquid acid grain, they will block the growth of chromium grain. And finally, there is a PET room appear in the bottom of the ingot. PET means chromium to effect transition. Also, in our simulation, the chromium phase is summed as cylinder, and the equiaxial grains are summed as ball or in our face. All faces are included. This is our main convolution equations. We can see that the mass transfer only occurs in the liquid phase, equiaxial grain, and columnar phase. And the amphibian transfer are existing between all these four phases. Also, the momentum in our simulation, the columnar is set as stationary. So the momentum compensation for columnar phase is missing. And here is the interaction between four phases. The mass and species transfer only occur from equator to equiaxial grain and equator to columnar grain. But the momentum and energy transfer are carried in all four phases. Here is the flow chart of the solution for each of computation, including the change equation such as this one, and the software equation, and the most important variable is the mass transfer rate during the simulation. in our simulation case, we use the user-defined adjustment macro to calculate the mass transfer rate firstly, and based on this rate, we can calculate the momentum transfer rate and energy transfer rate. And also we use the user-defined property to update the viscosity of solid phase. Here is the initial and boundary condition for our simulation. The ingot is about 4 meters high and 1.5 meters wide. It's about 55 tons, and here is the initial species fraction, and the initial temperature, and this is the boundary condition of this ingot.
And this is the steel, this is the copper steel, right?
Here is the carbon steel.
Right.
We only consider two elements in this simulation case. Actually, I think it's several, maybe
yes.
four.
May I add a little bit? So this is the large input for the copper steel here, that we want to understand the fluid flow during the casting, because this fluid flow is the origin of the micro. I think now it's macro segregation. So as you may imagine, the segregation is quite intimatal to the part. So simulate, thermo-soluto fluid flow. That means you get some dendritic growth, fluid flow, and also, as well as segregation profile. So what is the concentration, or what is the element that you are looking at? The distribution of the carbon, right? That's what.
Yes.
Right. Okay. Sure. So that is the aim of this one, in order to identify defect and try to minimize as much as possible. So thinking of, and this one has its real use actually for industry. So yeah. Sorry. Yeah. Please go ahead.
Okay. And here is our simulation result. And this figure shows the evolution of microstructure, and this one is liquid phase practice during the solidification. And this one is powder phase distributed during the solidification. And this one is liquid extra green.
Okay. So this one, yeah, this is not cell automata. It's based on the kind of indexes that you want to identify the morphology of the grain. So this is no real equax or columnar simulation, because this is 50 tons of steel. It's not impossible. So again, you need to understand. So they use the kind of variable to identify this columnar or equax, and then that is the location you would expect it to see. Imagine this is 1.5 meter long, and then about, is that 4 meter height, right? So it's a very large.
Yeah, 4 meters.
Yeah, so it's a very large part. But again, this to give you some idea what we do, why so matter. Segregation later you will see in the next cases in additive. But yeah, yes, please, sorry, please.
Okay. From the growth from the wall into the center, and eject the grain, nuclear, and feed down, and accumulated in the bottom of the ingot. And as we know, the carbon will be rejected in the liquid phase as the solidification progressing. So the concentration of carbon in liquid phase are increased during the solidification, and finally in the top of the area, the concentration of carbon is very high. Finally forming a positive microsegregation. Yeah. Also, during the solidification, the tissue cavity is forming in the top of the ingot. And based on this simulation result, we use this to compare with experimental results. And here is this one is the simulation result, and this one is experimental result. And we can see that both of them have the positive segregation in the top of the area, and there is a cone of the negative segregation in the bottom of the ingot. Here is sample print of real ingot. Both of them are the simulation results are in good agreement with the experimental results. It indicates that our model is relatively reliable. And then I will show how to build such complex model to reproduce this microstructure during the large scale ingot fabrication, and that will show the student mistake. And here is I think this is tutorial. Yeah, this one is the code. Very complex case. It's about 2,000 lines in this case.
So now it's not 10 line like previously. So we need to code up the equation that you showed before, 4 set of equation in this one, and then try to solve it. It's the same principle applied for additive as well, but probably additive is longer because you have complex of the boundary of, yeah. So just because I just look at the time, it's okay if you finish these cases and then we continue 2 cases in the next session. I think that would be good.
Yeah. And we should wrote A.
So how long does it take to calculate this part actually? I don't think it's going to be finished in...
I think at least 1 week.
1 week. So it's 1 week of calculation. Yeah. So I don't think we're going to make it. Yeah, but just show you. And I know if you are in the metallurgy field, you know how important of this profile is. And not many people around the world can do this, I believe. Yeah. It's quite complex geometry, and how accurate is another thing.
This is a proper original segregation, and this one is quantum negative segregation. And here is the code. And in this code,
easy code is
one. Yeah, this is the code. I think it's most important by this one. We want to get the mass transfer rate firstly, and based on this value, and we can calculate the species transfer and calculate the energy transfer. Energy transfer is here, and also this one is the thermal buoyancy.
Sure.
Yeah, and this function is used to calculate the number of nuclear engines.
So when you say number of nucleation, can I ask what is your definition, or what is your given condition for nucleation here? How did you define that?
I think it's based on the I should share the first.
It's actually just a normal distribution of the nuclei on the wall of the ingot, or is that something like that, right? I believe.
Yeah.
Okay. So you take that distribution from experiment, or what did you do? How did you define that? I think this is probably the question people here may want to know. Yeah.
This value, this result.
Yeah. Yes. Yeah.
The experimental result is provided by another movement.
And understand.
Yeah, because if we want to fabricate such a large, such larger scale because
Yes.
it will take a lot, will cost a lot of money.
Okay. So what
Yeah,
is the
it is.
assumption for that? Would that be you can you remember that? Is that for example, if this is steel, copper steel, right? So you're talking
Yeah.
about 30 to 50 micron average grain size that you as the initial condition, or what is that actually? So you just
Yeah.
randomly assign the seed of the nuclei at the wall of the ingot. Is that what you do?
Mm. Yeah.
Okay.
Also we neglect the pooling process during the simulation, and we assign the temperature at this value, and then begin to solidify.
Okay.
Mm.
Yeah, but anyway, this is just artificial, I would say, boundary for recreation, because it's not actually solve the density growth directly. You see this one, it just treat it as a set of phases that contain some property for that. And that's what I understand, right? Is what you, yeah, I think, okay, yeah, hopefully it's clarified. So I think probably this is a time for question before we finish this session. So we will continue the two cases, and then we will show more about density growth and the 3D printing next one. So what, do you have any question here for him? I can speak here. Please. I know you want to ask something? And anyone want to ask anything so far? So the one who used Fluent, I think Kishore is not here, I think. Oh, okay. You want to ask something? Are you trying to do simulation for additive as well? Have you experienced in the UDF?
Oh.
I'm asking the audience here.
No,
I know you so experienced. Yeah.
Actually, I'm working on CFD, sir.
Okay.
And lattice structures, fluid flow analysis.
Okay.
That's the.
Yeah, I mean there is an audience here. He doing some lattice structure, and then
Fluid
they
flow
try
analysis.
to use in Fluent. They try to understand the fluid flow allow that lattice structure. Is that something?
For finding of the permeabilities, sir.
Have you done any?
Yeah, I had done, sir.
Okay.
So that's why I want to discuss with you regarding
sure.
journey, sir. Return journey.
We can do something, yeah.
Yeah.
But that means you didn't print the structure. You just assume a structure that you see the fluid flow in this structure. Okay.
Yes.
It would be interesting what happened if this is actually an implant, for example. It would be an implant, right? And then you print it, and then with some surface roughness, this may be different, I believe, with the smooth surface that you have.
The last work was it take 45 days, sir, to me for last work in CFD simulation. 45 days.
45 days.
Yes,
I think it's too long.
Yes, sir.
I think Hong Kong.
Number of samples are more, sir.
Allowing within 1 week. I think. But
Number of
anyway,
samples
we can exchange some idea.
Yes, sir.
Yeah. Okay. Any other question before we finish this session? I think next one would be more exciting, and if you want to do more segregation, density growth, cellular growth, and then 3D printing, next one we will have a very exciting example. Say again? Which one? Yeah, that's isotropic material property. Yes. Yeah, for this one. Actually, is that correct, Hong Kong? We assume isotropic material property. So, but having said that, some casting cases for nickel superalloy as well as they can do some anisotropy property as well. But that is more another layer of complication. We didn't show it here, but definitely we will can discuss further on that. But because we can't show everything, so just give you some idea. So this density growth may be useful for the grain growth, and then especially we're going to have one paper with in Cornell Sen 18. So predict the lowest phase, which is the ECP, right? For the Inca 7A, which is the brittle arm movement. So we use a similar framework here, again for longer equation. I'm sure, but you going to show something like that here, or probably just mention briefly, right? Not completely. In the second cases, I believe. Hello, Hong Kong.
Okay.
Yes, yes. If not any question, I think we can come back in about hour. Hong Kong, I will. Please,
I know.
yeah, please connect in about 1 hour, and then we continue for case 2 and 3. Thank you very much.
Okay.
Thank you, and see you.
Thank you.
See you. Bye bye.
See you later.
Bye bye. Bye.
Bye.
So the lunch is arranged as usual, but there is a one special some non-veg item is also arranged. Somebody is non-veg vegetarians, so you can enjoy it. Yeah, thank you. Thank you. So we'll assemble back at 2 o'clock, and 2 to 3:30, and 3:30 we are going to local trip.
వెజిటేరియన్స్కి ఉంటుంది లేదు
you speak something, Hong Hao? Hello?
Yeah. Hello, Professor. Can you hear me?
Yeah, yeah. Not sure. Left, light.
No, ఇది ఆడియో జాక్
Yeah, that's what I think.
here.
Can you speak again? Hong Hao?
Yes, Professor. May I start now or a little later?
Yes.
అక్కడే ఉంది. One more
Okay.
time.
Can you speak?
Yes.
Hello?
Let's start.
Yeah, you can read the. Thank you very much.
Okay.
We were testing the
Okay.
sound. Yeah.
Oh, introduction of ANSYS FLUENT software.
Yes.
Is that okay?
Is that okay? He's speaking.
Simulation on the solidification of large scale records.
Can you speak again or play something?
Introduction of ANSYS FLUENT software. Simulation case 1.
ఎక్కడ పైన ఉందా? అది ఎక్కడుంటే అక్కడ పెట్టు.
Is that okay? Yeah. Have put.
Simulation on the solidification.
Okay, that's good. Okay, good.
Okay.
Yeah. So, shall we start? Do you think? Or we Yeah. So I think because we have time restriction, so we will start now. Hong Kao. Yeah. Please continue your
Okay.
presentation. Yes.
Okay, thank you. Thank you,
Thank you very
Professor. Hello, everyone. I will continue my presentation now, and I will show the next simulation case. It's about a simulation on the dendritic grain grow. In this case, we will consider the magnetic field assisted solidification. Magnetic field assisted solidification is important for many process technologies, such as directional solidification. Here is a schematic description of directional solidification. During the solidification, the external magnetic field affects the microstructure by influencing the matter flow, heat transfer, and solute transport process. The directional solidification experiment inside Bridgman furnace. This is a Bridgman furnace, and the thermal gradient was imposed by heating element. This one is the heating element, and the cooling system in the bottom of the sample. Both of the heating element and the cooling system to keep the sample with a constant thermal gradient during the whole experiment. And also, the K-type thermocouples were used to monitor the temperature and adjust the temperature. And this one is the final microstructure characteristics after the metal solidifier. And because of the effect of the magnetic field applying on the metal liquid when it's solidified. So there are several physical phenomena occur in this solidification process. And it was as we know that the application of a standard magnetic field will inhibit the metal flow due to the Hartmann effect. However, in our simulation, in this case, the application of standard magnetic fields during the solidification has also been found to drive the metal flow through the dendrite. The effect we call it is thermoelectromagnetic force, which always generated by the feedback effect. And what's the feedback effect? We know that like the thermocouples, the temperature, we know that the metal with a different temperature and with different temperature, and they has different feedback coefficient. And so in the because solid and liquid has a different temperature distribution, and also their feedback coefficients are different. So in the surface of solid and liquid interface, there will be a thermoelectric current occur. Yeah. So under this thermoelectric current and the magnetic field, the liquid will flow under the Lorentz force. Yeah. So
I think just to set the scene for the people participant here for this problem, I think as you know, we have some research in additive manufacturing with we call field assisted. So we use electromagnetic field as well doing the deposition of the additive. So I think this may be relevant or applicable to that context, how the dendritic behavior during that, I mean, when we combine. So that's mean Hong Kao going to explain to us, we need to add another equation on top of this one to take into account the magnetic field. Yes, please.
Yeah.
Thank you.
Okay. And in our simulation, the main conservation equation are presented in this slide, and here system is the thermoelectromagnetic force, and in this case, only two phases are taken into account: the liquid phase and solid phase. The solid phase is stationary, which means the velocity of the which means the velocity is zero, and the liquid phase are movements, and the velocity is solved by this equation, and this one is the thermal solute buoyancy force during the solidification, which will drive the liquid flow in the simulation domain. And also, this case is built based on cellular automata method covered with multiple phase approach. And here I want to introduce the cellular automata approach. The cubic grid cell was used in current model. We know that the cellular automata method, before we use this approach, we want to define the state of the cell. And in our simulation, we define 3 states of cell. The first one is liquid and interface, and the third one is solid state. And the solid state cell have a solid phase fraction of unity. Means the phase fraction is 1, while liquid cells is a solid phase fraction of 0. And the liquid flow only occur in liquid cells and interface cells. And the interface cell has the ability to catch the liquid cells, and with the solidification progress, the interface will change to the solid cells. Here is the flow chart of the different cells. They will change their state by this flow chart. And also, I want to introduce is the that if this the blue one is the interface cell, there will be a square appear in this cell during the solidification of the interface cell. The square will grow bigger when they touch the navel cells. Usually the navel cells is the liquid cells, and the interface will catch the navel cell as interface 2. And meanwhile, there's a square appear too. During the solidification, these squares will grow up and catch the navel cells. Finally, the interface cells lose the capture ability when it changes to a solid cell. As the state and the solid volume fraction updated, the progress of the melting solidification is predicted, which means we use this progress to simulate the dendritic grains grow. And in this simulation, we will use this macros. And here is the initial and the boundary condition for our simulation. There are 3 nucleus in the bottom of the bottom of the simulation domain, and also we will apply a thermal gradient with 6,000 K per meter. And the left wall and the right wall is pressure out. And this is the initial temperature and the cooling rate of this simulation. And here is the evolution of dendritic growth. And we can find that this case is without magnetic field. This one is under magnetic field. And the main difference is that the max velocity of liquid in this case is larger than without magnetic field. It's about 0.0017 meter per second. It's much larger than this case. And also we found that here we can see the symmetrical characteristic of secondary dendrite. And in this case, it's symmetrical. It changes the characteristic of the grain.
Yeah, so I have few questions here, Hong Kao. On the first three figure on the left hand side, this is the without magnetic field, right? Or with
yes.
The left hand side, this is no magnetic field, and the right hand side has magnetic field. Is that right?
Yes. Yes.
And this is one question. The second one is actually, what is the material system we are looking at now?
This is aluminum and copper.
Aluminum copper alloy. So aluminum.
Yeah,
copper.
aluminum copper alloy. Yeah.
Yeah, and then you are looking at the segregation profile of the copper. Is that correct?
Yes.
Okay.
Copper is a species.
Okay.
Yeah.
Yeah. Thank you.
And we also see the T02 interface appeared in this case on the magnetic field. Also, the experimental results also show the similar results that we can see in this picture. And then I will show how to build this simulation case use the FLUENT, ANSYS FLUENT.
Yes,
and then.
So I believe you also will show as well the code that used or customized for these cases as well, right? That you need to compile to set up this, right?
Yeah.
That's good. Cool. So this is different from the previous cases in the sense that we implement another computational approach, which is say CA or cellular automata, combined with those four equations that we use. Is that correct? That is the differences.
Yes.
Okay, sure.
And in this case, we use the Euler multi-phase.
Yeah, multi-phase Eulerian framework. That's we use here.
Yeah, and we will open the energy equation, and here is the material, and also the property of material are written by the UDF.
So this is
And
the thermophysical property for each phases, right? That you define for the system. So we have about 7 phases, I see previously. So you have aluminum, liquid, solid, something like that, and then copper, liquid, solid, and then what? Yeah, that's right.
we should create a ISO interface and
What we are looking now is a temperature history. Sorry, temperature distribution, temperature field, I think, right?
here is the
Dendrite.
dendrite, and then they will grow up and then as the solidification progress, they will grow up again, and like that. And here is the code. Code, I think, is in the most important part is.
Okay, sure.
In this part, we apply this force. We call it thermal electromagnetic force in here, and we use the defined sources micro to add the force. The force is in 3 directions. Here is the x direction and y direction and z direction. Z direction. Also, we consider the thermal buoyancy, thermal through buoyancy. This one is thermal convection, and this one is through convection. And our results also can see the.
Okay. Yes. So this one, I have another question. You actually simulating the alloy system, aluminum copper. How you take into account the segregation then? In terms of you will need to have aluminum and copper separately, and then you do some calculation about the thermodynamic kind of behavior, right? Did you incorporate this here or no? It's just
sorry. What's the question?
Yeah, did you actually consider thermodynamic for aluminum copper system here?
It's a binary.
Okay, so it's actually in your code as well?
Yeah, it's a binary alloy.
Okay.
Okay. Yeah, aluminum and copper. I think.
This is through material property, right?
Yeah, this part is material property, and we can define the density, specific heat, and something else.
So this material property calculated from the thermodynamic software, I believe, as a temperature-dependent property. Is that right?
Yes.
So basically, you calculate a phase diagram some way, somehow, and then import that into this model, and then kicks out everything.
Yeah.
Is that correct?
Yes, I will always use the GMAT Pro. This software. Yes.
So anyway, this is actually a bit weakly coupled approach. Do you think we can do strong couple? Let's say let the software communicate with each other and then feedback the kinetics. because this maybe actually have kinetic. Is that how can we take into account the kinetic into this problem actually? Sorry for asking. Is that relevant question? I believe to, yeah. I'm not going to examine him, but just asking the question for the benefit of everyone. I believe it's useful. Yeah, sorry for asking too many, but I think this is important information.
Yes, I think so.
You will appreciate that this is not simple calculation. It's need to communicate with many software, many coding, programming. Even you have the, I think not too cheap software packages. Yeah, you still need to work a lot. But the thing is, you have developer to help you to, debugging the code if you pay more to get a new version. But our job is to worry about equation. Yeah, but if you do open source, probably everything depends on you, how good or bad like me at the beginning. So it's run very slow because we don't have people to help on other aspects. But anyway, yeah, so you want to show JMAT Pro what you did for the aluminum copper system, or what? I think I saw you open the JMAT Pro. What do you want to say?
Yeah, and in JMAT Pro we can input the concentration of the element, and then we can run. We always use the solidification part, and then we run the JMAT Pro and get the density, and we can.
That means this actually depend on the available database for this material system. I think this is a problem. It depends on how you buy this software, which company you select actually to get better. This also come with cost, I think. Yeah, but currently we use this software JMAT Pro. But some application for me, we use other thermodynamic software packages as well. So as you know, you will expect different database.
Yes, and the software can provide the density.
But that is assumption made by
liquid viscosity and thermal conductivity.
So this is all the thermal physical property temperature dependent, right?
Yeah. Yes.
Sure.
Yeah.
So, but if the temperature go over, let's say in this graph, go over 1000 Kelvin, so you will need to be, extrapolate or approximate it, right? To be, that is also another point for the thermophysical property as well.
Yeah, and
close
the.
So let's say you export the table, like the graph, it will be probably tabulated or function whatsoever, and then you call the temperature when needed at the centroid of the temperature field, so that you don't need to worry about. It's just about the value of temperature and assign the property of that. I think that is usually standard approach we do. Let the computer working on it. Anyway, thank you very much. So what you want to show next, please? Hong Hao, please continue if you.
Okay, I will close this one, and we'll to the next simulation case. And next simulation case, I will introduce the additive manufacturing. And the first one is the LDD, which I has measured in previous slide. LDD is short of laser directed energy deposition. That use focused laser beam to metal and deposit material. Typically, it's a particle. Sometimes we will use a wire. And in this slide, this is the LDD process, and we use a high-speed camera to record the deposition. And we can see that the powder particle flow from the nozzle, and some particles rebound back, and some particles flow into the metal pool and remelted. And also some particles into the metal pool and flow around the liquid. And the LDD process always deposition on a material directly onto an existing part or substrate. Here is the substrate. And so it's very important to introduce it's very important to investigate the flow, heat, and mass transfer in the metal pool. And we also build several simulation cases to investigate the physical phenomena during the LDD. Here is the microscopic equations, and include mass conservation equation, and the momentum conservation, and energy conservation equations. These two simulation cases show the temperature distribution, and also the metal pool evolutions. In this case, we present the dendrite growth during the metal pool solidification. Also, we can obtain the result of microstructure characteristics. And and then in our simulation, we have built two cases. Between these cases, we want to use the temperature data to link each other. And first, we acquire the temperature from the microscale multiple model, and then we use this temperature data. We transfer this temperature data to the micro scale model. For the micro scale model, we also use the cellular automata method. And in this simulation case, the green structure, salutar segregation, and the dendrite structure are all will be considered. And here is the flow chart for the temperature transfer from this model to a CA coupling model. And also we do some experimental result. Do some experimental, and comparison of the cross-sectional morphology of the metal pool from the experimental and our simulation results. The material used in this experiment and simulation is a kind of super alloying. And this is the parameter for the experimental and simulation.
So
Yeah,
this is super alloy. This is super.
Yeah.
Right. And what is the super alloy here? Is that 718?
Yeah, Inconel 718.
Okay, this is Inconel 718.
Yeah, and here is the microscopic simulation results. The evolution of temperature distribution and the metal pool are presented in these figures. And after that, the temperature will be outputted when the metal pool is stable, such as for this time, and the temperature will outputted to the micro scale simulation case. And the temperature will be linear interpolated from the microscopic temperature field to the micro temperature field. And later I will show the code how to make this linear interpolations.
Yeah, so basically when you want to basically link from the macroscopic temperature field from oily multiphase solver, you need to approximate, you need to export this temperature field to the cell automata, right?
Yes.
But it's still, there is a, I would say probably we say problem, because there's a mismatch between the match in the temperature field, which is normally larger than the match, because you are capturing the dendritics scale. So we are now, this is another numerical treatment that we need some way somehow to interpolate the temperature in between, because let's say your mesh is 1 millimeter and you want to do 1 micron, something like that. So that means you need to interpolate the temperature in between. Yeah. So yeah, that's what it's doing. Yeah. Thank you. Yes.
And here is the simulation result. We can see that this part is the substrate microstructure characteristics, and we can see some grains has epitaxial growth, and also some equiaxial grain nucleation here, and the columnar and the equiaxial similar the columnar grain and the equiaxial grains will competitive growth. Finally, in the top of the metal, in the top of the metal pool, the columnar to the equiaxial transition is found. And the primary, the PDS is the primary dendrite arm space and grain structure for simulation results and experimental results are compared with each other. And the result shows they are in good agreement. And also we compared the experimental results in this figure, which is the EVSD result.
So
And
so you are looking at the dendritic growth on the top left hand side here, and then looking at the segregation profile of niobium, right? This niobium is actually the important segregation profile for lava space, right? And then you're looking at for different location in the mel pool, I believe that is in the mel pool, right? This 10 for the bottom. This is only one deposition, one layer.
One layer.
Only
just
one
layer.
So okay, So this is only one layer. You see some differences here, and then you compare this result with the EDX measurement. Is that right?
Yes, this is the EVSD measurement.
And this is the result on the bottom left here that you see simulated and then experiment. Okay, thank you. So basically the qualitative comparison, not exactly match, but it's in the same trend, I believe. Yeah, sure, that's good. So yes, please.
And then I will show the simulation cases, both of macroscopic and microscopic.
Sure, please. Please.
Okay. And we click the place.
So this is a macroscopic model that you're talking about. This is thermo-soluto fluid flow, right?
Yes. Here is the temperature distribution result, and I will add the velocity of liquid flow is here. And we can see that the liquid flow from the center to the side of the metal pool because of the magnetic force. And here this one is and this is hold for this case.
Okay. So this is a macro, right? Or this is both of them combined?
And if after this simulation, we output the temperature history to the macro microscopic simulation is here. This one.
This is what? This is the cell automata, right? This is a micro.
Yes, cell automata and the linear, and here is the temperature from the
previous
model. Temperature.
Mm.
Temperature from the macro, and we will do some linear interpolation. Yes, interpolation and get the according the coordinate and the time, and we will calculate the temperature. Such as
this is the temperature field for every time step. Is that right?
Yes, every time step.
Consider.
But
so
we use the coordinator and flow time to calculate the current time in the specific cell.
Okay. And this actually, yes. So you take about a quarter or 1/4 or half of the melt pool, is that right? You simulate half of it.
Yes, only half.
Only half. So basically, he saved some result each for particular time step to show us. Now I think load some result. So you may appreciate that this is a huge data that generated from this kind of this kind of simulation. But that's
the mesh
the
size
data processing is something you also need to code up to basically get this data to be similar to run the video as well, I believe, right? As another layer of coding. Yeah. Only 2D.
Yes.
But we will show next
slide only
3D. But you will see here how surprising the dendrite actually break up and then form the equax grain at the top. This is how the transition from columnar to equax grains happen. So this simulation gives very detailed insight what happened. Yes.
Yes, here is the microsegregation during the multiple solidification. Yeah, we can see the species, the elements are enriched in the liquid area during the solidification, like here. And
yeah, this is automatically coming out from simulation. We didn't assign anything. Just let it go. Yeah, but under the representative temperature history, this may behave differently. Yeah. So that's what it is. And again, just to remind you, this is aluminum copper. This may be different from nickel, I believe. Anyway, thank you very much. I think I just watched the time. I think it's probably interesting to briefly explain the last cases now with the powder-based fusion additive that we are working on at the moment. Yeah, I mean, he just want to show how detailed you can get with the niobium segregation profile. To me, it looks like a micrograph that you can take from PDS or yes, yeah. So that's what the level of modeling we're interested in. We like to do in this kind of simulation because these simulations length scale that we are looking at provide extra information from normal simulation like heat. So you won't be able to measure this easily. I mean, doing printing. I'm sure, right? So not yet, no one measure the microstructure evolution during 3D printing yet, as far as I know. Yeah. So this is an opportunity that we can get further, especially if the part is quite complicated, but not too complicated. We can replicate what happened as well. I mean, again, yeah. Thank you very much, Hokao. I think, shall we move to the last one with the powder-based fusion, in situ alloying? Yeah. Yes, please.
Okay.
Yes. Do you assume the black diffusion of the solute, back diffusion, right?
Yes.
Did you? Okay, yes, he did. So you can find more information. I think it's not published yet, right? This the one you show. We are going to publish this one, I believe. The work you just show on the dendritic growth there is not published yet. Is that right?
Yes.
Okay, so we can share with you later when once published. But there's some other paper talking about niobium segregation profile as well. It's not just us. I think, yeah. But anyway, this is the powder-based fusion now.
Okay.
Yes.
Here is a laser powder bed fusion. We call it LPBF. It's another typical additive manufacturing process. And that use a high-powered laser and selectively remelt powdered material layer by layer. Nowadays, scientists use synchrotron X-ray to observe the physical phenomena during the LPBF process. Here is the simple result. And X-ray will penetrate the sample, and there is a monitor behind the sample, and will receive the signal. Different materials have different capability to absorb the X-ray intensity, and finally, the monitor receive different signal to observe the metal evolution. In this result, we can find that due to the laser shock, some particles are flown away, and some particles are remelted and become melted liquid, and the melt pool is forming gradually. And because of the surface tension, the liquid always looks like a ball, I think. And then we want to do some simulation about LPBF. Firstly, we should build the conservation equations. In this simulations, multi-phase model was considered, including the liquid phase and the air. The volume of fluid method was used to check the interface between these two phases. And for this equation is about the energy conservation. This one is the laser heat energy, and these three terms is about the heat loss during the progress and this one is convection, and this one is radiation, and this one is evaporation. And also, we use the momentum conservation equation to obtain the velocity of liquid. Here, the liquid is metal, and in this equation, this one is the density term, and this one is the surface tension term, and the magnetic force and the coin pressure, which arise from the evaporations. And this is the physical parameter for our simulation, including the laser pulse, scan speed, and laser thickness, and so on. And this is the initial and the boundary conditions for this simulation. Here is the result of evolution of metal pool and the temperature field. We can use the cross section to describe the evolution later. And this one is the volume fraction of liquid, and this is the temperature distribution. And the temperature, this one, and multiple and the velocity distribution are presented in these two pictures. The solid metal particles were gradually heated by the laser to form a multiple, and the shape of the multiple was basically stable after a period of time. Due to the extremely high laser energy density, and here, like here, a distinct concave shape is forming in this area. If the laser energy large enough, the keyhole will form, I think. As the laser spot moved, the liquid metal gradually cooled and solidified to form a solidified check, like this area. And sometimes there's okay, and also I will show the simulation result by the ANSYS FLUENT software.
This is the pure element, right? The material you are looking at here is a single material.
Yes.
Okay, sure. Yeah, what is the can you comment on the computational resources used for this simulation? match. Oh, element. I think there are two models, right? The first one is the macroscopic, right? Oh, in this case, you don't do any cell automata. So this is a hexagonal match. Is that correct? Or
Yes.
Yeah, it's hex match.
Hex match.
Hex match. Yeah. So, but cell automata is also hex match as well. But some CFD it will be tetragonal, which is again depends. But you can use hex match in crystal plasticity as well. But
Fixing the hexahedral mesh system within the powder particles, it must be difficult. Is it because it
good
won't?
question. So it will be about approximately about 5 elements across minimum. And because this is interface capturing, because what we see, we will. I think he didn't mention at the beginning. It will be the whole calculation domain, and then we identify some boundary to be a phases for metal. Someone is for the air. So during that interface definition, we will class across the hex match. It's not because some element will be because it's volume of fluid, it's strict volume. So it will be can contain both phases at the same time. So it doesn't matter. It's a moving interface problem. Yeah. So it's not fixed interface.
So
You see what I mean, right? Because in one element you can have both phases existing at the same time.
Correct, understand.
Its volume is fixed.
Volume.
Yeah, volume. Finite volume. Yeah. Okay. Next, please.
And and for this case, this one is manganese force, and this is recoil pressure force in this simulation case, and also they has 3 directional X, Y, and Z. And we can see that and and in this case, the volume of fluid method is used to check the interface between liquid and the sample.
Right.
And yes, and also the liquid flow is some the laminar flow.
It's laminar flow. Okay, good.
Yes. Also, here.
What is the mesh size here?
Mesh size is about let me check. 4 micrometer.
4 micron. Not too
Yeah.
small. I mean, I see. Yeah, probably in CA you may need smaller mesh size, I think.
Yes.
I mean, we did some CA, so it will be probably 1 micron for CA, right?
CA, I think is 1 micrometer or
60,
smaller than.
64
Yeah.
times lower, so more very high resolution. But anyway, it's about right. It's about in order to 5 to 10. It depends on how big your domain is. But at the moment, for the conventional CFD like this, we not tend to apply adaptive match because it would be so problematic. But now people try to use this for the very extremely complicated detailed dynamics that they want to know. Yeah, but that's it. Leave it for another matter. That's related to more computational technique. Yeah.
do we need to change the discretization scheme for each of the term in momentum equation in order to get proper more realization of the physics? I just want to know discretization scheme like Gaussian, linear, all those things. Forward.
At the moment, it's not changing. Well,
Okay.
I don't understand your question actually.
Okay, so
Okay, he asked, do we need to change this criticization scheme for each
term,
relation or
each term in the mass conservation equation and
I
momentum
don't think
conservation
so.
equation?
because everything, I mean, the equation there is described for any phase. Because the principle of the finite or volume of fluid principle is actually you have an element. This element can contain up to 100 phase if you want. But describe only use single equation set that describe for what happened. But you would have another phase equation, which is alpha equal to alpha 1 plus alpha 2, which is alpha 1 is the gases or metallic and plus gas, and then you use that to describe, and then the equation is for alpha. It will split to alpha 1, alpha 2, alpha 3, alpha 4, whatsoever. It's number of phases you're looking at, but you use single equation to describe. Is that correct?
Yes.
Yeah, this is called volume of fluid. But there is another technique that we may consider the phase separately. Again, you use a different equation to explain. I can't remember exactly how it's called, but that is another numerical technique you use. So okay, A is A, B and this is B, something like that. But I think that is probably the case for us. So we use a single set of equation to express the behavior of each phase.
Okay, thank you. Thank you.
Thank you. But this is traditional as well. And then I think this probably a very first time, apart from you go to, or probably not, in the software training, when you decide to buy them, they will go to such a great detail. Otherwise, it will be very high level description of the model. Especially some paper, I don't want to say much, but this is, I mean, reality. Let's say early paper in this area, published from a national lab from USA. They didn't actually say any equation about how they derive this, but just show the result. Okay, I'm doing this. Yeah. So it's not actually what we want. We want to make it as open as possible, but to some extent, not everything, because it's still, we need to publish something, right? So is that finished, Hong Kao, or you are going to wrap up or what? Yeah.
And at the end of the lecture, I want to share my experience to use the ANSYS FLUENT.
Yes, please.
Especially on about the UDF function, I think.
Okay.
Yeah. Usually I will use the this manual.
Okay. Yeah.
Yeah,
So
to find
manual.
yes, use this manual to find which micro we want to use and what's the description or the usage and where to load or link the macro. Yes, for example, if we want to define the property of different material, and we can find
Information here, right?
yeah, we can find this macro, and they will provide the description of this macro, and also they will say we can define the density viscosity and thermal conductivity, and after that, they will provide the usage, and there are three arguments we want to define or we want to provide, and here is the name of the properties, such as, for example,
Yes, sure.
yes, I will define the density of alloy based on my simulation case, and also these two arguments will be provided or will be transferred from the ANSYS FLUENT to this code. So we didn't redefine this argument, and also so I think the most important thing is that they will provide us the example to tell us how to use this macro. For example, in this example, it's about a temperature-dependent viscosity property, and which means viscosity is varied by the temperature, and then they will provide the full code in here, and we can copy this code to our own file and make some modify or revise, and we can use this code successfully.
Sure.
Yes, yes, they will provide us several examples, and also they will tell us where to hook the UDF, and for example, they will tell us the property will be used in this dialog box.
Yes.
Yes, and
yeah, thank you very much for this one. I think we probably have a few minutes left here. Can you actually present the last slide? So I appreciate that this is actually something we can, it's come with times, the skill and experience on this. If you are a PhD student or researcher, I think it's not just happen in one day or 1 month. It's actually the experience that you build over time, and hope appreciate that. So having said that, Hong Kao, can you summarize what we learned for today? Yeah.
Okay, thank you. Today I prepare a brief presentation about our research, mostly focused on the solidification from casting to additive manufacturing, and we learn the evolutionary mechanism of microsegregation for large-scale ingots. Also, we learn the effect of magnetic field on the dendritic grains growth. And furthermore, the manifold is predicted in our additive manufacturing process. Finally, I think our model can be used to predict the precipitation and something like crystal plasticity, and so on. Also, the external field can be derived from magnetic or electric field, and so on. And thank you very much for the listening, and that.
Thank you very much.
Okay.
Thank you. So very good. So thank you, Hong Kao. I think we will finish here, and then we'll catch up with you later. Thank you.
Okay.
Thank you very much.
Yeah, thank you very much. So I appreciate that. Yeah, so it's like case studies which we understood a lot from your PhD student. Thank you very much for that. And now, so yeah, the bus is ready at outside. So we are moving to the local trip. Before that, we'll have a small refreshments. Yeah, we'll wait for 5 minutes for the refreshments will come. And once we take the refreshments, then we'll proceed for the local trip. And for tomorrow, anything you can announce? Okay. So I hope everybody has corrected your name on the against your the certificates. So then all the best for your examination who opted for the credits, right? Anything else you want to let me know? Anything? Okay, let me know. Do you have any questions in general or technical? Maybe for 5 minutes we can spend. Please, Arun. You were not there yesterday? Yes. Yeah, that we have rescheduled it. Rescheduled in the sense like we are not going to do that one. He is asking some labs. Yeah. So we have 2 more sessions from here. Yes. Yeah, then I think we have 2 more lab sessions. That is tomorrow. Yeah. Anybody have some questions? Yeah, so tomorrow will be like first 2 sessions, 3 sessions will be here after lunch. So we are going to have at the lab, additive manufacturing lab, that is one is printing as well as post-processing. Both the lab sessions will be there at the additive manufacturing lab. Yeah, we are going to divide the 3 batches. Now itself you want to divide? Serial number 1. 3 batches. So you know your number, serial number 1 to 20. You know the numbers, right? So you have a unique number. So serial number 1 to 20, we have 1 batch. 21 to 40, 41 to 60. 3 batches. We'll go in 3 batches. So, yeah. Okay, then we'll take a break and then we'll take refreshments outside and immediately we'll move on to the, so we'll call for the day today. Okay, thank you.